Welcome to Paris Course number 133, and today we're talking about an interesting flow control device on an airfoil. So this comes from an idea with birds. So we have a picture here in figure 1 of a seagull landing. And if you look at a lot of birds, not just seagulls, but a lot of birds in general, if you look at the back wings when the bird is landing, often there will be these feathers that pop up. So there will be these two sets of feathers, one underneath and one on top. And this is thought to be some sort of flow control device. So that's what we're going to be looking at today. And this is called a Bionic Airfoil. And to do so, we're going to be looking at a paper called Numerical Simulation of Flow over Bionic Airfoils. And this is open access. You can find it in the link in the description. So let's start here. So these feathers, as I mentioned, can pop up for the trailing edge. And there are two surfaces effectively. And these are two sets of trailing edge feathers in essence. So this study focuses on the effects of this type of setup on the aerodynamic performance of a wing. And they have a little schematic here showing the idealized situation of this, so the idealized cross section, where you have the trailing edge, which comes down as a typical trailing edge on an airfoil. But then a little bit further upstream on the suction surface of this airfoil, so the upper surface, you have this additional little platform that comes out, this flap. And this, they've drawn it as being flat, so it comes straight out horizontally, but it can be at different angles. So these birds, for example, they can put them up at different angles, a little bit higher, a little bit lower, depending on their aerodynamic needs. And we're not really sure yet what these effects are, but we will cover in this paper what they are. So by the end of this podcast, we will know what they do. So this paper includes not only the angle that these flaps are angled at, but also the shape of the flaps and also how far up they are pitched or pitched down and how far up the airfoil they are located. And to do that, they're looking at this airfoil called an HQ17 airfoil. So let's have a look at this cross section. In figure 2, we can see this CFD setup here, which has the mesh over it, and we'll cover the CFD in a second. I just wanted to show this HQ17 airfoil because it is quite an unusual one. Like, it's not very common. In fact, I actually had to look up this airfoil because I wasn't too sure about its geometry. And it has a maximum thickness of 15.2% occurring at 42% of the chord, which is quite far downstream. Usually the maximum thickness occurs around 25% for a typical run-of-the-mill airfoil. So this is a little bit different to most airfoils. Also, it has a maximum camber of 4.5% occurring at 42% of the chord again. So where we have the maximum thickness, we also get the maximum chord. So that's quite interesting. Now, looking up the performance of this airfoil, I looked it up in some books and that, and I found that the maximum lift coefficient is usually around 1.3. In this research, they found a very similar result, which we'll cover in a second. The minimum drag coefficient is 0.01 often. So that's really good. So we have quite a run-of-the-mill lift coefficient, but we have a very low drag coefficient, and this is somewhat expected considering this is quite a thick airfoil, so we do get like the flow accelerating quite a lot over the top, and it will come down quite nicely with the pressure drag being quite low, at low angles of attack at least. Now, because it is cambered, it means that we do have a lift being produced at non-zero degree angles of attack. So what about the RANs of the CFD? Let's talk about that. So they used a RAN setup, and it was steady, so it wasn't URANs, it was just regular RANs, which is fine because, for the clean airfoil, it is definitely fine because there's not really much three-dimensional flow going on here. And they also looked at a two-dimensional situation, so the 3D aspects are not really considered here. They used an SST turbulence model, which is quite good. It's definitely a step up from the two-equation turbulence models like K omega and K epsilon. And with this, you typically want to have a Y plus of 1. That's for the SST approach. And the good thing is that they did do that. Now, they used a C-grid mesh, and this is quite important because it allows you to pitch the angle of the airfoil at different angles of attack effectively without having to change your mesh. So let me describe what this means. I'll draw it a little bit so we can get a better idea. And for those who are listening to this on Spotify and or Google, you can watch the video on
drawing here. If you're not watching this, you can go onto our YouTube channel and also see some other goodies which we do every week and almost every day. So this C-grid topology, if we have a typical CFD box, then we have the front is this curve, so it's a C. Then we have the airfoil inside. And the reason why this C inlet is quite important is because if we were to have just a regular flat box, like a flat front, a square front,
then if we wanted to change the angle of attack of the airfoil, we then need to literally change the geometry. So we need to change it to whatever angle of attack we want. With this approach with the C grid, all we have to do is just say, okay, the air is coming in at different angles. And because we have this corner, the bottom corner here, it meets quite nicely with the wall, the side. We don't have to worry about flow separation around here. Whereas if we were to do the same thing with the rectangular CFD box, if we were to put like an angle of attack like this of the air coming in, the flow would separate around this point and would get quite a lot of problems with the boundary conditions that we're specifying with the sidewall here. So by having the C grid topology, we can change the angle of attack of the airfoil very easily, literally by just changing the solver settings. We just say, okay, we're putting the angle of attack at, we're saying that the flow is not coming in at 5 meters per second horizontally, it's 5 meters per second at 3 degrees, 5 degrees, 10 degrees, whatever. That way we can keep the same mesh. It cuts down on meshing time and it solves a lot of problems that way. So that's quite nice. So now the Reynolds number was 1 million and the Mach number was 0.1. So the reason why the Mach number is quite important is because if you have the Mach number 0.3 or more as a rule of thumb, we say that the flow is now compressible. The reason why we say that is because at a Mach number of 0.3 or above, the density of air will change by about 2% or more because the flow in front of the airfoil is now being squished, or whatever object we have. The reason why is because air can only really move so fast. It is heavily dictated by its viscosity. And if you look at the equation for determining the velocity of air, the speed of sound, you look at it's based on the gas constant, the temperature, and the ratio of specific heats. So these are different quantities that do affect how fast the flow can move. And if we go too fast, so above a Mach number of 0.3, we may not be getting shocks, but we will be getting to the point where the flow isn't really moving quickly enough to be able to move to the point where it's not really being, it's not incompressible. Now, even at Mach 0.3, the flow is still being compressed by about 2%, the density is increasing by that much, and that's still quite a decent error, but that's just the rule of thumb that has come down to us over the years. Now, if you go to Mach 0.2, I think the density changes are like not even 1%, so that's even better. But that's just the rule of thumb we use. So Mach number of 0.1 is quite good. It means that we have almost no change in the density, so that's quite good. Now, the validation of this CFD was done against, for the baseline airfoil, was done against some experimental results. And they show this in figure 2. Now, the experimental results were taken from another study, and they found that for the lift coefficient, there is really good agreement. So we can see here in this pre-stall angles of attack, the lift coefficient matches almost identically with the experimental data. Even in the stall regime and the post-stall regime, the lift coefficient produced is very similar to the experimental data, so that's quite nice. And the maximum lift coefficient we achieve here is about 1.35, 1.4, which is a little bit higher than I found in some textbooks, but those textbooks only went up to like 250,000 Reynolds number, so this is 1 billion Reynolds number. So that makes sense that we get a slightly higher lift coefficient. So we get good agreement here. Now, one thing that they didn't give us is the drag coefficient validation. And that may be a problem because I'm pretty sure that in the experimental data here, they didn't take into account the changes in the density of air throughout the experiments, because it does change throughout the day and between days, weeks, months, and seasons. So if we have changes in the density of air here, that is then going to change the forces that we measure and also the velocity of the wind tunnel that we're running it at. So if we don't know what the density change is, so if it's like 1.2 kilograms instead of 1.21 or whatever, then when we do our CFD, we can't take into account those errors or those changes, and we get errors in the CFD. It's not going to line up. So whether the CFD matched the experimental data in terms of the drag coefficient or not, we don't know, but there is a good chance that it didn't because the density of air was not taken into account, I'm pretty sure. So it might have been a couple % error there overall. So let's move on to the actual effects of these flaps. So in figure 3, we see the general effect of just a flap in general around the trailing edge section. So we have the trailing edge, and then just above that, upstream, we have this flap just coming out pretty much horizontally. And one thing I should compliment the researchers on is that they did quite a nice mesh around this flap and the trailing edge. So trailing edges for airfoils are quite difficult to do to begin with because they do come down in this angle, and that means that the cells that are made around them become very heavily skewed. They often have very high aspect ratios and result in low quality cells. So to get around that, you need to have quite a fine mesh, like cell layers. And to make this even harder for this airfoil, they have this flap coming out. And this flap is literally just a flat plate, so it has almost no thickness. And that is also hard to mesh as well, because when you get to the trailing edge, you now have these two cells that have to meet up over a very discrete and small change in thicknesses. So if you have a slight thickness to the flap, that could then mean that you have to have very fine cells around here. So the researchers did quite nicely with this mesh here, I think. But anyway, let's talk about the general effects of this flap. So just a regular flap in general that is horizontally coming out of the airfoil around the trailing edge, the lift coefficient is modified in a couple of ways. So we can see here in figure 3b. First, the maximum lift coefficient achieved is much greater when we have a flap. Instead of about 1.4, we get about 1.55, so that's really nice. We get an increase in that maximum lift coefficient. The second thing is that the lift coefficient slope is shifted to the right a little. So less lift is being produced at the same pre-stall angle of attack. We can see here when we had like 0 degrees angle of attack, for example, when we had just the clean wing, we had a lift coefficient of 0.6. But for the wing with a flap at 0 degree angle of attack, we have like a lift coefficient of about 0.25 now, or maybe even 0.2. So it's a massive reduction. That means that we've kind of reduced the effective angle of attack, you could say, of the airfoil by about 4 degrees, which means that what the airfoil's lift coefficient is being produced with this flap is pretty much the same as the clean airfoil at 4 degrees lower angle of attack, if that makes sense. So that's just the general idea of what this flap does, but there are a lot of different things that we can do to this flap to see how it affects the flow and the aerodynamics of the airfoil. One thing we can do is change the layout of the flap. So here they kept the flap the same length of 20% of the airfoil's chord length. So in other words, they have the flap starting at 80% of the chord, and then it goes all the way to the trailing edge, it looks like. And then they just pitched it up and down from horizontally down to 5.71 degrees and up to 12.14 degrees and in between. So what does that do to the aerodynamics of this airfoil? So before we go any further, just pause this and think to yourself what this might do. And then once you've done that, let's come back to the podcast and we'll start up again. So I have assumed that you've paused the podcast and thought about what this is doing to the airfoil's aerodynamics by pitching this flap at different angles of attack. Let's continue on to what it does. So in figure 6, they show the effects of the different flap angles for the lift coefficient. So CL minus CL base. In other words, if you have a negative value, it's reducing the lift at the angle of attack. If you have a positive value, it's increasing the lift. So first, they looked at when the airfoil had no gap, so the flap was right on the airfoil surface connected to it. And for the lift coefficient, regardless of the flap's angle, the exact same trend occurred, namely a reduced lift coefficient at pre-stall angles of attack, but increased maximum lift coefficients and delayed stall. So we can see here in figures 6a and 6b, the baseline airfoil is this solid black line, whereas all the dashed lines are for the flap at different angles of attack. And regardless of this angle, at pre-stall angles of attack, so below like 10 degrees, the airfoils had a worse lift coefficient. But once we get to the stall and post-stall regimes, the airfoils increased the lift coefficient. And that's what we found with the general trend before. So one question that we have is, why would this flap delay stall? Because here what we're seeing is we're getting higher lift coefficients, and the point at which the stall occurs is at a high angle attack. Why does that occur? Well, figure 8 shows why. So let's move down to that briefly. So if we look at these, we can see that the pressure coefficients are plotted. And when we get to the trailing edge section, the pressure coefficient moves closer to 0. So what we see here is with the baseline, which is this solid black line, it's at like 0, minus 0.3, minus 0.35. Whereas for the dashed ones, we can see that it's significantly lower, it's significantly greater. It's minus 0.3, minus 0.25. So that means that the adverse pressure gradient is lower. So if the adverse pressure gradient is lower, it means that the flow can stay attached for high angles of attack, which is why we delay stall. And that's what's happening with this flap. And while it may seem like an interesting result, it isn't really that surprising, because anytime you mess with the trailing edge of an airfoil, you're probably going to affect the adverse pressure gradient, and that affects the stall characteristics as well. I also saw another flow control device that did something similar to this, but it was quite a different geometry, and it was probably about 10 years ago now. So I was in a conference once, and this professor was, who's from Singapore University, I think. He was like presenting some results on this airfoil, which was like a normal airfoil, except you had the suction surface towards the trailing edge cut out. So you had like this massive part removed in the trailing edge section. And this also delayed stall. And the reason why is because when you remove that little section, you reduce the adverse pressure gradient, which means that the flow can stay attached to higher angles of attack. The same general thing occurs here, and it's a different geometry altogether. So it's quite interesting that they have two different geometries, but they occur in the same general region, and they affect the adverse pressure gradient to a similar sort of extent, and the lift coefficient as well. So what about the drag coefficient? So in figure 7, they also go into this as well. And interestingly, at pre-stall angles of attack, the flap increases the drag coefficient, which again isn't that surprising considering that this flap makes the trailing edge have a larger wake and hence a greater pressure drag. So let me draw this to sort of explain what I mean by this, because it may not be that obvious just from discussing it. So let's go back into Paint here.
Show you what I mean. So if we have this airfoil, then we have the flow coming over the top, and it might separate towards the trailing edge perhaps. The angle of attack might be too high. So we get a wake maybe this great. Now if we have the exact same situation, we have the airfoil here, and we have a flap coming out now, and the flow comes over. Well, look at this. The flow has to go over, which means that now we have a wake which is much greater. So just because we have a greater wake means that we are going to be getting a greater pressure drag, and that means we get a greater drag overall. So it's not surprising that this flap does increase the drag. But what about the post-stall regime? So we know that in the post-stall regime, the lift coefficient is quite favorable. In fact, this flap significantly increases the lift coefficient overall. And this also comes at the benefit of the drag coefficient. So we can see that the drag coefficient is also reduced in this post-stall regime. And that kind of makes sense, because if we don't get stall, it means that we're not getting this increase in the pressure drag in this regime. So in the pre-stall regime, the flap can be sort of seen as reducing the performance of the airfoil. In the post-stall regime, it's sort of increasing it. So that's often a trade-off that we do have to make sometimes. And if you want to make it, at least, if you don't like it, don't use the flap. You can use something else. So in addition to this flap being attached and pitched at different angles, the researchers here also looked at curving the flaps to a different way. So you have this straight flap which comes out horizontally, but they also looked at these flaps that are curved. So they have two different types. The first is an S-shaped flap that has a peak first, then a trough. The second one is, again, an S-shaped flap, but it has a trough first and then a peak. So you can see this trough here, then a peak, as opposed to a peak here, then a trough. A few questions arise. One, is this S shape going to make a difference? And two, is the peak first going to make a difference, or is the trough first going to make a difference, or does it really matter? So that's what these researchers looked into. So let's look at figure 11, which shows the effects on the lift and drag coefficients. So interestingly, in the post-stall regime, changing the flap's geometry like this had almost no effect on these coefficients. So you can see that they almost completely match each other. And they did increase the lift performance in the post-stall regime, as you'd expect with these flaps, as we've seen already. And the drag is also reduced. But in the pre-stall regime, we do get some changes. So now we can see that these different dash lines correspond to different flaps. S0 is the straight flap. S1 is the flap where we have the peak first, trough second. S2 is where we have the trough first, then the peak. So what is happening here? So the S-shaped flap with the peak first and then the trough has the greatest effects on the lift and drag coefficients. We can see that this is modeled as this dashed black line. So this one here and this one here for the drag. For the pre-stall regime, the lift is being reduced the most by this flap, and in the drag, it's increasing the drag the most in this regime. So that's not good. On the other hand, when we have the S-shaped flap with the trough first and then the peak, the lift reduction is not as bad as either of the other two flaps, and the drag increase is not as bad either. So in other words, this one is pretty good. Then we have the straight flap, which has like the horizontal flap, no curve to it at all. The performance of this falls somewhere in between. So depending on how
bad you want to make your airfoil, I guess, you can choose either one of these flaps. But in other words, if you want to reduce the negative effects of the flap, go for S2, which means you have the trough first, then the peak. So why does this happen? Why do we get such a variation? Well, the researchers weren't quite clear about why this occurred. And I think they may have also mislabeled some of the figures down here. So they showed some streamlines where we had S0, which has the straight bit here. S1, they have the curve here, but they have the trough first and the peak. This should be peak first, then trough. I think this should be S2, and it should be labeled S1. So I'm not really sure what's going on with these figures, but from what I can tell, having the S shape effectively changes how much of the airfoil is producing a wake. For the flat flap, you can have a certain amount of wake. Then for the S-shaped flap, when the peak comes first, so let's go back up to these figures first. This one here, when we have the peak first, then the trough. Well, if the flow hits the peak first, and then that could create a bigger wake. So the flow sort of detaches here perhaps and makes a bigger wake in general here. And the opposite is true for the S-shaped one where we have the trough first, then the peak. So the flow may come down, stay attached quite nicely. Then when we get to this point, it then detaches a little bit and we get a smaller wake, but there is still a bit of wake here. So that's why I think we do get these changes based on these different shapes, which weren't that clear in these streamlined figures here because I'm not sure what's going on with these labelings, if it's accurate or not. I don't think it is accurate. But that's what I think is happening. Now, another thing they looked at was moving the flaps to different heights, so away from the actual airfoil surface. We're not going to go into that in this podcast. In the next podcast, we'll cover it. What we're going to do now is recap what these flaps do. So in conclusion to this podcast, we've looked at the flaps, the effects of these flaps when you pop them up from the airfoil surface. We found that, or these researchers found, I guess you should say, that the flap on the suction side of an airfoil near the trailing edge reduces the lift coefficient and increases the drag coefficient in the pre-still regimes. So you can see here reductions and increases in the drag coefficients respectively, lift and drag coefficients respectively. In the post-still regimes, the lift and drag coefficients are improved, so we get an increase in the lift and a reduction in the drag. That's really nice. The more the flap is pitched up, the greater effect it has, including making the airfoil perform worse at pre-still angles of attack and perform better at post-still angles of attack. So let's go back up to these figures here, where we have different angles of attack, and we can see that the more aggressive the angle of attack is, the more the reduction of the lift is in the pre-still, but also the post-still is more favorable. Curving the flap into an S shape, and not just being flat, has a slight effect in the pre-still regime, and if the peak comes first, that effect is detrimental. So we can see here that this dashed black line, because we have the peak first, it has a worse performance than any of the other flaps. If we have the trough coming first, that is then going to produce a better performing airfoil in the pre-still regime and has almost no effect in the post-still. So we're getting all the benefit with a reduced negative. So that's the end of this podcast. And if you liked it, make sure to like it. And if you want to see more like this, make sure to subscribe or follow on Spotify or whatever. And check out the playlist that we have for our podcasts. We've done 133 of them now, so that's pretty sweet. And if you want to make your experience better by 2 to 4%, check out Atmosphere Hawk. Remember how I talked about earlier in the podcast how the density of air changes from day to day, week to week, month to month, season to season, and even within a day. The density of air can change by 2 to 4% quite easily on a regular day. And when you use experimental data to validate your CFD like these researchers did, chances are that they didn't do that, so the data is erroneous, and you need to take into account the changes in the density of air if you want to make your CFD line up well. That may be one reason why we didn't see the drag coefficient being validated here. If you want to make your experiments better, check out the Atmosphere Hawk. It's an instrument we make to accurately measure the density of air for you, and it prints it quite nicely, and it integrates straight into MATLAB and LabVIEW and C++ and Python and Java. We have all the codes for it, and you can find it in the link in the description. And if you want to get better at CFD and or theory yourself, check out our courses in the link in the description, and I'll see you next podcast. Peace, amigos.